So the first thing we have to do is to think about what does this assembly language program do? So I'm going to talk a little bit about what an assembly language program looks like and sort of walk you through, very briefly, the process by which that ASCII file gets translated into the binary representation of the sequence of instructions. This chicken and the egg problem is pretty interesting. If you're starting off with a raw machine, what do you write the assembler in? I mean, you can say, I want to write an assembler so I can write assembly language programs so I can run them on the machine, but the assembler is a program, and what does it run in? And thankfully what happens is typically when there's a brand new shiny piece of hardware, I go back to the machine I've been using and I actually write a cross assembler. I write something that on my old machine will read an assembly language program and translate it into binary for the new machine, and then I can assemble the assembler and run everything natively on the new machine. But how did that start? There must have been a time when there was no assembler and somebody must have keyed in the binary for the assembler, and in fact that's what happened. When I first started using machines, I won't say how long ago, the way you started a machine is you sat down at the console and actually, using buttons, keyed in a set of little instructions directly into memory, the binary representation of the instructions into memory, which would cause it to read the paper tape, which would then load the rest of memory, and away we'd go, right? So we knew a lot more about assembly language in the old days than we seem to have to know now. Okay, so what does an assembly language program look like? Well, the simplest sort of assembly language program is just a list of numbers. And we can write them in decimal or binary or hexadecimal, whatever is convenient for us. And the assembly program just takes each one of these numbers and turns them into, in this case, 8 bits worth of memory. So this, I can take this binary representation and I can come up with an 8-bit pattern that is then put in binary pattern, which becomes the value of the next byte of memory. So this particular sequence of 1, 2, 3, 4, 5 values would represent the binary pattern that will appear, the integer representation of the binary pattern that will appear in 5 consecutive bytes of memory. Okay, now of course just constants are a little tedious, so I'm going to want to be able to write expressions instead of just simple numbers. So in fact the assembler allows you to use the standard sort of simple operators, plus, minus, times, this is logical and, so forth and so on. And of course all of these evaluate in their different ways to the actual number 23, which has a very particular binary pattern which could appear in a byte. Now, very quickly you get tired of imagining just, you can say, well, this is going to be a big help, Chris. I mean, so instead of actually keying the values into memory, I can write them out in text, and now I have a program that will translate them from a text representation of the number into the actual binary bits. And you say, well, that doesn't seem very helpful. So we're going to now do something that will get us a lot closer to writing, things like add of R2, R3, R4. So the first thing I'm going to introduce is this notion of symbols, a symbolic representation for a numeric value. We'll discover that that'll make things a lot easier. And the way the assembler works with that is it's going to build itself a symbol table. And a symbol table is just a data structure that takes the name of a symbol, for instance, X, and it associates it with a particular value, in this case hex 1000, like so. And so whenever, then when I could write an expression like x plus 1, and what the assembler will do is says, oh, the symbol x, I need to get its value. It will go to the symbol table and say, oh, he's using x currently to be the symbolic representation of this number 1000. So the assembler would know to translate this into the hex number 1001. That makes sense? So we're just, and you can sort of say, well, why bother give a symbolic name to something? And one, it will help us make the program easier to read. For example, when I'm referring to registers, I almost always use the symbolic name of the register, like R0. And I mean, at the bottom, at the end of the day, the assembler is going to want a 5-bit value to stick in that field. You could have written an integer or an expression, 3 plus 2. And you can say, aha, see, that's my clever way of talking about R5. But you'll find it be much more easy for other people to read your program if you actually wrote R5 and someone say, well, R5 is the name of a symbol, which somewhere in my symbol table okay, is associated with the actual numeric value 5. And if you look, you can see the beginnings of a bunch of statements which are actually buried inside beta.uasm, which appears at the front, is included at the front of all your assembly language programs, that set up a bunch of symbols for you to use to make your program a little easier to read and write. Okay. We'll see very quickly another use for symbols, but this is just, you can say, okay, so that sounds convenient, Chris. Well, I'm sort of skeptical, yet I want to write an assembly language. You can introduce comments in an assembly language program by using this vertical bar that from there to the end of the line those characters are not treated as directives to the assembler. Those are just treated as comments that are ignored by the assembler. Okay, we have a special symbol called dot. So one of the entries in the symbol table is a symbol that's spelled just with the letter period. And that represents the next location to be filled in memory by the assembler. So when you start running the assembler, dot is initially 0, and every time the assembler evaluates an expression and gets an 8-bit value and puts that value in memory, it puts it at the location pointed to by dot. So it says, okay, what's dot? Oh, 0. So this next byte I've assembled goes in location 0. And after it does that, and it increases dot by 1, and says, okay, the next byte I fill will be at address 1. So dot is just sort of this little finger the assembler is using to keep track of where it's putting stuff in memory. And so this basically says, okay, dear Mr. Assembler, please set dot to hex 100, which means I want you to start filling memory at byte hex 100. And then here's some values, 1, 2, 3, 4. And now you can sort of see, this expression here basically says, oh, the symbol 5, so we're going to add a new entry to my symbol table. So this got low, so as I put, dot was 100, and then it's 101, 102, 103. So now dot is 104, hex 104. And now that directive, which defines the value 5 to be equal to whatever the value of whatever that expression is. So on the other side of the equal sign, there's an expression. In this case, it's the single symbol dot, which has the value hex 104. Okay, and the most common thing we use symbol for is to remember a memory address so we can reference it later. Because it turns out that we're going to need a memory addresses to know where the beginnings of procedures are or where in memory a particular variable lives. And when we write an assembly language, what we're going to do is to ask the assembler, we're going to give a symbolic name to the address of that location, and for thereafter we won't deal with addresses at all. We'll simply just use that symbolic name for the address of a particular location, which holds an instruction or a piece of data. Okay, so you can see some more examples here. Now this x equals dot, you'd see a lot when we're doing assembly language programs. So in fact, we have a special abbreviation where we just use the name of the symbol colon, and you know that to mean, look, please make the value of the symbol x equal to the address of the location that I'm sort of at the current place in my assembly language program. So for example, I'm setting dot to hex 1000, so I'm expecting to fill up memory starting at byte hex 1000. This squares dot says, please remember the address of this location. Okay, and you can say, well, why didn't I just set it to 1000? This seems a little redundant. Well, the point is that typically you're going along and you have a whole bunch of statements which are filling up memory. You don't exactly know how much room they take, so you don't actually know precisely what the value of the squares is, but you do know you want it to be the address of the location holding that 0. That makes sense? So what we're doing is just saying, look, please, Mr. Assembler, please remember where you are. Tell me, you know where you are. You've been filling up memory. Just remember, take that value, the address of where you are in memory, the value of the symbol dot, and store it away in a separate name so that I can refer to it in the future. So I can later on use the value SQRS, the symbol squares in an expression, to refer to the address of that location. Okay, so here's a bunch of expressions that fill up 16 different bytes. You can see 16 different bytes. And you can see the bytes slowly being filled in one by one. And then there's this long guy here. I'll show you about macros in a second. This is a macro call with this numeric argument. And what that's doing is actually computing the distance between where I am now and where the array started, which actually has the values, the difference between those two values is 16. There were 16 bytes that got filled. And so that number 16 is actually encoded in 4 consecutive bytes there.